Hey everyone, how you doing? Welcome to Practical Math B, real-world math applied to finance and economics. For week 8, we're going to be analyzing the business cycle and learning about how we can use piecewise functions to do that. So here's our essential question. How can we write a function that might describe the United States' current economy, and how can we compare it with the economy historically? We're going to be learning how changes in economic conditions affect real GDP. We're going to generalize the business cycle as a piecewise function. We're going to discuss the business cycle in terms of a function. And we're going to find the extrema of a function and use it to compare economic conditions. Take notes while we're going through this video. Pause it, work with stuff. The examples I go over are going to be similar problems you'll see on the lesson quiz for this week. There's also a text you can read to learn more about this topic, and use this video as a text as an open resource while working on all the assignments. Let me know if you have any other questions. Here we go. So how do we measure the economic growth of a country? Well, we could look at how much they sell, right? We could look at how much they export, how much goods go out to other countries. We could look at, well, how much do people buy in the country? Or we could try and measure how much people make. There's lots of different ways to measure economic growth. The one we're going to be learning about today is what's called GDP. GDP just stands for gross domestic product. And no, it's not gross like as in yucky. It's like total is gross. Total domestic product. How much total domestic are we making at our home product, producing? It's one way we measure economic growth of a country. So GDP is the market value of all the final goods and services produced in a country in a calendar year. And it's used to determine the size of the economy at a point in time. So we're going to be going throughout this video, we're going to be looking at the gross domestic product growth of the US over time for like the last 100 years or so, and see if we can apply math with linear equations or linear functions and quadratic functions. That's what you're working on in week 8 for your algebra review. So we're going to apply some of this stuff with linear and quadratic to look for patterns in the economic growth of our country. But before we do that, let's watch a little video just to help us understand more about what the GDP is.
The Federal Reserve Bank of St. Louis presents the Economic Lowdown. LOL, IDK, XOXO, BFF, TTYL, GDP. Were you stumped by the last acronym? GDP stands for Gross Domestic Product. You probably don't see many references to it on social media, but GDP conveys an important message on the economy. Economists use this measurement to tell the story of the economy. They use GDP to determine the size of the economy at a point in time and growth of the economy over time. GDP measures the total market value of all final goods and services produced in an economy in a given year. Goods are items that are touchable, such as appliances, cars, and clothing. Services are actions, things people do for us, such as haircuts, car repairs, and customer service. Let's take a look at 3 phrases used to define GDP. The first phrase is total market value. The value of a good or service is determined by the price paid for that item in the marketplace. When you add those prices together, you have the total value of GDP. The second phrase is final goods and services. The use of final in this phrase refers to goods and services sold to an end user. Let's look at it this way. Tires are sold to a company that produces automobiles. Those tires installed on a new car are not counted in GDP. Why? Because the tires are not a final good. The tires are an intermediate good, a good used in the production of final goods and services. The value of the tires will be reflected in the total price of the car when it's sold to the end user. However, when new tires are purchased by the end user to replace the worn-out tires on the car, this value is counted in GDP. Those tires are a final good because they were sold to the end user. The third and final phrase is produced within an economy. Only goods and services produced within a country's borders count in that nation's GDP. So, to be counted in U.S. GDP, something must be produced within the borders of the United States. GDP does not take the national ownership of the business that produces the good or service into consideration. So, a car produced in Kentucky counts as U.S. GDP even if it's produced by a foreign company. But a car produced in Mexico does not count as U.S. GDP even if it's produced by a U.S. company. So GDP measures the size of the economy, the total market value of all final goods and services produced within an economy in a given year. GDP is among the most important and widely reported pieces of economic data. A wide variety of people, from business owners to policymakers, use GDP in decision-making. Economists use actual market prices to calculate the value of GDP. And as you know, prices are constantly changing, and those changing prices can make it difficult to understand a change in GDP. For example, an increase in GDP could mean any of the following. A, the country has produced more goods and services. B, the country has produced the same amount of goods and services, but the prices of those goods and services have increased. Or C, the country has some combination of more goods and services produced and higher prices. GDP can be looked at two different ways. When GDP is presented in its unadjusted form, it's called nominal GDP. To calculate the real increase or decrease over time in the level of final goods and services, price changes are removed from GDP data. The revised measurement is called real GDP. So real GDP is GDP adjusted for inflation and more accurately reflects the actual increase or decrease in output, that is, production of goods and services. Economists measure economic growth by comparing real GDP over time. Economic growth is usually presented as a percentage increase or decrease from an earlier period. And, as we've already learned, it's important to adjust GDP for inflation. For example, it might be useful to know that nominal GDP in the third quarter of 2013 was $16.9 trillion, but it's probably more meaningful to know that real GDP increased by, or the economy grew by, an annual rate of 4.1% in the third quarter of 2013. Real GDP removes the effects of price changes, but to discuss growth, we focus on the percent increase in real GDP instead of the total value or level of GDP. To put that 4.1% in context, consider that real GDP has grown at an average annual rate of 3.3% since 1950. Remember, however, that 3.3% is an average taken over a long time period. GDP has a tendency to bounce around a bit from quarter to quarter. A general rule of thumb is that 2 consecutive quarters of declining real GDP constitute a recession. Although economists have more comprehensive ways to determine the phases of the business cycle, this rule of thumb is widely used. In short, GDP is central to our understanding of the state of the economy. In addition to measuring the economy, GDP can be used to indicate, on average, the standard of living for people in different countries. Because goods and services are sold for money, and money earned in producing goods and services is income, GDP is a measure of national income. To determine the impact of national income on individual people, GDP is divided by the country's population. The resulting measurement is GDP per person and is most commonly called GDP per capita. For example, think of 2 countries, Alpha and Omega, with comparable GDPs, say $200 billion each. One might assume that the citizens of Alpha and Omega have similar standard of living because their countries have comparable GDPs. But what if Alpha has a population of 200 million people and Omega has a population of 5 million people? Because Alpha's GDP is divided among a much larger population, each person's share is much smaller. In this case, Alpha's GDP per capita is $1,000, while Omega's is $40,000. So while their GDPs are the same, once they're divided by the population, it's easier to see a dramatic difference in the standard of living in these 2 nations. Notice, though, that GDP per capita is an average. The actual earnings of individual people will likely vary greatly depending on the distribution of income. Changes in real GDP per capita within the same country can be used to estimate changes in the standard of living over time. An increase in real GDP per capita over time is interpreted as an increase in the standard of living, a worthy goal for any society. GDP helps us identify growth in an economy, and a growing economy is an economy that produces more and more goods and services for its population. And, generally speaking, more is better. GDP data are among the most important economic data available, but measuring the output of a large, dynamic economy is a complex task. GDP measures production levels during a period of time and can be adjusted for inflation, a measure called real GDP. And real GDP can be compared with earlier periods to evaluate economic growth. All things being equal, growth is good, and GDP measures growth. This video was produced by the Federal Reserve Bank of St. Louis. For more information, visit us online at stlouisfed.org.
All right, so quick review. Again, the GDP is the market value of all final goods and services produced in a country within that calendar year and is used to determine the size of the economy at a point in time. So some key words to point out. We have what's called market value, right? When we say the GDP is the market value, it's the price paid for a good or service in the marketplace. We also have to emphasize, well, what does final goods and services mean? Final goods and services are goods and services produced for consumers or end users. An example of that would be when people purchase flour at the store to produce cookies or bread at home. It's part of the real GDP. They're purchasing flour. Flour is a final good. However, if that flour is sold directly to a bakery, and then that bakery produces baked goods, such as bread or donuts or cookies or whatever, then the flour is no longer a final good. It's a intermediate good. We'll get to that next. But the baked good itself, when the bakery sells that cake, that is the actual final good. And that's what's counted as part of the real GDP. So you have to be able to distinguish what is a final good or not. For example, intermediate goods are not counted as part of the real GDP, but go into the production of a good or service. So that would be when the flour for the bread at the bakery, that flour doesn't count as far as the GDP does, but the bread that the bakery sells, that would be. All right, so a quick review on some words there. Let's look at some examples. Let's play a game. Part of GDP or not? Is eating out at your favorite local restaurant part of the GDP, part of our country's gross domestic product? What do you think? Well, yes, you are consuming a good produced locally. The local restaurant is selling you some dinner, so yes, that's part of our GDP. If you go out to Red Robin, you get a milkshake and a burger, you're contributing to the gross domestic product. What about if you go to the service station and they change your flat tire for you? Yes, that would be part of the GDP. You are a consumer, they're giving you a service, charging you probably for that service. If you go to Les Schwab, not, but there you go. It's part of GDP. What if a dad changes the flat tire on his kid's bike? It's a service being performed, but no, this would not be part of the GDP. The dad is not going to charge the kid to change his flat tire. There's no market value with that. What if an Italian, they vacation in New York City? They stay at a hotel, they fly over, they go to restaurants, they buy things. Is this part of our GDP? Well, yes, it would be. Because in New York City, we are selling a good, producing and selling a good to the Italian who's purchasing it in New York. So yes, that's part of our country's GDP. However, if you go on a trip to Japan and you buy a bracelet while you're there, you are spending your money. There is a market value, but it is not produced locally in our nation. So no, we would be contributing to the GDP of Japan if that was the case. All right. Bread sold to a family in Kansas. They go to their local grocery market. They buy a loaf of bread. Is that part of the gross domestic product? Yes, it is. That family is going to consume it and they paid a value for it. However, bread sold to McDonald's to produce cheeseburgers, the cheeseburger is the final product. The bread sold to McDonald's is part of the production, so it is not part of the GDP. Hopefully you get an idea of what a final good is now and what an intermediate good is and what actually contributes to how we measure or tally up this value of GDP. So what affects the GDP? If growing it is so important, what kind of things affect the growth? Well, there's business investment. If the economy is growing, Businesses tend to expand and spend more money on new plants and equipment. They produce more products, they hire more workers, and all of that is money that affects final goods or produces final goods, or people are able to afford to buy goods. When the economy is contracting, businesses spend less, they reduce production, they lay off workers. So businesses have a big effect on the GDP, right? Consumer expectations. If consumers expect the economy to expand, resulting in more jobs and increases in income, then they'll likely spend more. We kind of have seen this recently, right? If people are feeling confident, they spend more at Christmas, they spend more for birthdays, they go to vacations. But if people are feeling like things are not good in the economy, then they'll postpone that vacation, they'll cut back, they'll try and save money. And if they're not buying things, then businesses are not making money or they're contracting. So consumer expectation is a big thing that affects the GDP a lot as well. Interest rates and credit. When interest rates are low, businesses tend to borrow to make new investments. People are willing to buy a house when interest rates are low. People buy more things if they can use interest and credit to help do those things. However, when interest rates rise, it gets really expensive to do business loans. It gets really expensive to get the money you need to produce things, and so they're less likely. So interest rates and credit have a big effect on the gross domestic product as well. And finally, there's just things that happen, external shocks, a drought, a disruption of the oil supply, a hurricane, things like that that negatively impact the economy. If there's a drought in California and they're not able to produce all the fruits and vegetables that they normally do, that raises the prices, which makes things more expensive, which means people don't buy as much, and it just affects the overall economy. So here's some headlines. Think about what would happen if this thing actually happened. A new home construction falls for the third quarter. Would that be a mark of increasing or decreasing GDP? Well, if construction falls, that means houses are not being built. That means businesses are contracting. It means they're not investing as much money into workers. They're not investing as much money into purchasing the construction materials. People are not buying houses. That is an indicator that the GDP is decreasing. Investment spending continues to grow. Well, what does that mean? Well, investment is when businesses or banks or other people are taking their money and they're feeling like, yes, I need to invest my money, put my money out there to spend things I want to try and make money. So people are freer with their money. They're investing it. Other people are using that money to produce things. That would be a sign of increasing the GDP. Money is flowing. Investments are happening. People are buying and selling. All right, hopefully at this point you have a pretty good sense now of what we're talking about when we talk about GDP, gross domestic product. So now here's where it gets fun. Let's transition into doing some math. Here's a graph showing a business cycle of increase and decrease in GDP. What math functions, if you think about all the things that we've learned in your algebra classes, math classes, what functions could we use to model what we see? What's going on here in this graph? Well, if you look at the graph as a whole, it kind of goes up and down and waves and flats and curves and all sorts of things. So in math, sometimes it's helpful to break it into sections. So we've got these little dotted lines here. And let's look at section by section. This first section right here, I'm going to call it number 1. If we just look at this part, what kind of graph does that look like? Well, it looks like the parabolas that you've been exploring now this week, right? Kind of goes up, makes a little upside down U, and then it comes up like that, right? So we would call that a quadratic equation. We're going to do some stuff with quadratic equations today and in this lesson to help us learn stuff. And quadratic equations always have a vertex. Now let's look at section 2. Can't switch colors, but that's all right. So section 2, what do we have going on here? Well, between these parts, between these x values, it again kind of looks like another quadratic equation, but instead of going up and then down, it goes down then up. So it's kind of showing the reverse. So it's another quadratic. It's got another vertex right there, but it's going down and up. And then finally, what do we have in section 3? What does this look like? Well, looks like just a linear equation, right? It's got slope, a straight line. So if I wanted to model what was going on here, we would need 3 different equations, 3 different functions, and we would put them all together, and we would call that a piecewise function. Piecewise function means we just take several functions, mash them together to make one big function. Okay, let's think about what these mean a little bit. What is going on? If this represents the business cycle, what is happening between 1 and 4.5? Well, usually the x-axis measures years, right? GDP is how many years go by, and this y-axis represents how much money. So if we look at over this period as the years go by in the beginning, things are growing, right? Things are growing. Businesses are doing good. The GDP is increasing. We're making more money. We're producing more things until we hit this maximum point, and then things start to slide. We get a recession going down. And then the recession continues. People are losing jobs. People are getting laid off. People are not buying things. It's really stressful, and we hit rock bottom. There's a minimum point, a vertex right there. But things eventually turn around. Stuff starts to happen. We contract, but we start to increase again. And then we see things increasing, increasing, and increasing. So we have a whole growth period. So we can look at this as in terms of there's periods of recession, there's periods of growth, and we're going to use math to help us model those and make sense of what's going on.
The U.S. economy has enjoyed long-term growth, but at times that growth has been interrupted by periods of recession or even depression. The term business cycles is used to describe fluctuations that tend to occur in economies. While the duration and intensity of these fluctuations vary greatly between individual cycles, all of them display the same pattern. The first phase of the business cycle is the peak. This is the point at which the economy has reached its temporary maximum. The second phase is the recession. In this phase, we can see a period of decline in the total output of the economy. This phase is also usually accompanied by increased unemployment. The trough is the point at which the recession levels off, and output and employment are at their lowest levels. After the economy has reached bottom, the recovery phase occurs. In this phase, output and employment levels begin to rise again. Let's look at some historical behavior of the U.S. economy and identify the phases of the business cycle.
Okay, here we are. We have a business cycle down here. We can see we got from 1930 to 1939. These are my years. Here's my real gross domestic product. That means it's just accounted for inflation in billions of dollars. We can see from 1929, things were not doing good, right? We declined. We hit rock bottom in 1932. Things were stressful. And then they started to get a little bit better again. Things got a little bit better, kind of peaked around 1937, quick little recession, and then boom. All of a sudden we started improving. What we're going to do is we're going to make a piecewise function of this period of time, and we're going to use some functions to represent what's going on. So first thing we got to do is figure out what's our first piece. Let me get a pen, get a pen color. The first piece, if I look at this, I'm going to say right here in 1936 seems to be a good split where we have kind of a parabola going on. Fill it in there. So I'm going to use a quadratic equation. Now, one thing you've hopefully learned about in algebra classes is we have what's called the vertex form of a quadratic equation. I'm going to put the general form in my function. A vertex form, you have some coefficient a, which tells you does your graph open up or open down, times x minus h squared, the squared is what makes it quadratic, plus k. Now that's called our vertex form because the vertex is this value h and k. And it's the easiest one. If we know what the vertex is, it's the easiest one to come up with an equation for. So if we look at this parabola right here, the vertex is either the very minimum or maximum point. If I look at this, the vertex here, I'm going to write it down. The vertex on our particular section is at 1932. There was a value of 750. That was the gross domestic product. 750 billions of dollars. That's how much our country produced that year. All right, we got a vertex. That's my h and k. So if I start to fill things in, where are we at now? We've got my function f of x equals some constant a times x minus h is the x value of the vertex. I'm going to put in 1932 squared plus k is the y value, 750. Now we're fixing our parabola to go through that exact point and are calling it the vertex. Now I'm not all the way there though. I still got to figure out what is this value for a, right? Well, to do that I need another point that it goes through. So I'm going to use this point right here, 1936. That's an x value. And if I put that x value into the function, we get a function value, f of x, of 1000. That's one of the points on this parabola, and I want it to go through that. So I want it to have a minimum there and also go through that point. Well, what I do then is I just put 1936 in for x, because that's an x value I know I want it to go through. And I put 1000 in for f of x, because that's the function. When I put in 1936 for x, calculate it all out, I'm going to get a value of 1000. So what ends up happening is we know everything. We get an equation like this, 1000 equals a times 1936 minus 1932 squared plus 750. Now look what we got. We have a whole equation. And the only thing I don't know is this value for a, but we can solve that. We know how to solve an equation to figure out what a needs to be. So let's do some work and solve for what a needs to be. If I subtract 1936 minus 1932, that's going to become 4. So it becomes a times 4 squared plus 750 equals 1000. 4 squared is 16, so that's just 16 times a plus 750 equals 1000. Now it's a two-step equation. I'm going to subtract 750 from both sides. We got 250 equals 16a. And finally, if I divide both sides by 16, we get that a is equal to 15.625. And we now have our function, a mathematical function that goes through these points is going to be f of x is equal to 15.625. It's a positive value for a, which is going to mean my graph is going to go up, times x minus 1932, oops, I didn't space this out very well, squared, and then there's a plus 750 on the end. Now, there's my function, but I only want a piece of it, right? That's not the entire thing, so I need to designate, I need to say that this function only works for the values of x that are greater than 1929, because I'm not given any information beyond 1929. I don't know what happens out here. So from 1929 up to 1936, and I'm going to include equals 1936, that's when this function works. So I'm just taking a piece of it over these x values. Between 1929 and 1936, use this function. All right, we got piece number 1 done. But we got some more, right? So let's take a look now at piece number 2. What do we got going on over here? Well, piece number 2 starts at 1936. And looks like we have kind of another curve thing going on right here, right? Not exactly, but again, this is how we use math to kind of predict as well as we could. And it's kind of another, oh, there's 1936 right here. Let me go back. All right, here we are on piece number 2. So, what do we got now? Let's take a look. I'm going to switch colors. Let's do this one in red. So from number 2, the last one went up to 1936, right? So this one is going to start at 1936, and we have another little curve thing going on, right? In fact, it looks like another little parabola. So it's another quadratic function. This one has a vertex. Where's the maximum point? Instead of opening up and going down with a minimum point, this one is opening down with a maximum point. But the maximum point is at 1937. Things peaked at $1,100 billion, or $1,100,000,000. So we got a vertex point. There's my H and there's my K. Let's pull back our vertex form again. All quadratic equations can be written in vertex form just like this. So we've got H and K, we're almost good. I just need another point. So I used 1936 and 1,000 last time. Let's use 1938 and 1,000 this time. We'll use this as our second point. So now I'm going to write a function for this parabola going from 1936 to 1938. It's going to be my second piece of the function. So again, putting my vertex in, we get a times x minus 1937 squared plus 1,100 is my function. For my second point, in my x value, I'm going to put 1938. And from my function value at 1938, my function has to be 1,000. And so now we've got this equation that we can solve. 1,000 equals a times 1938 minus 1937 squared plus 1,100. I'm going to do the same steps to solve it because I need to figure out what is this coefficient a that determines where my parabola goes. Well, let's do it. 1938 minus 1937 is just 1, and 1 squared is 1. So this actually simplifies pretty nicely. We got 1,000 equals 1 times a, which is just a, plus 1,100. If we subtract 1,100 from both sides, we see that a just equals negative 100. So now we've got a function for the second part. The second function, I'm going to call it g, just to keep it different than the first function f. G of x, the second part in red, is a quadratic equation. It's negative 100 times x minus 1937. It has a different vertex than the other one, squared, plus 1,100. And we're going to use this function. We just want the piece of it. So it's going to go from 1936. And I want the x values greater than 1936 up to 1938. I want it to stop at 1938. So there we go. There's my second piece of the function. So we got the first one is a quadratic. The second one is a quadratic. Let's go tackle this third piece now. All right, the third piece. What do we got going on here? Let's get a different color now, and let's do some magenta. So the third piece, we went from 1938, and the rest of the graph, it's just a straight line, right? This is going to be a linear function. So linear function means we need to figure out the slope. And then we have, for linear function, we can write it in point slope form. It equals your slope m times x minus x1 plus y1. x1 and y1 are just a point that it goes through. So we're going to use this point right here for 1940. That's going to be my x value to go through, and 1500, that's going to be my y value. For m, we just need 2 points to find the slope, so let's start with that. Let's find the slope. If I look at the 2 points, I'm going to subtract my y values. So I need to do 1500 minus 1100. And that was an increase. So, whoops, not 1100, 1000. Read the wrong point. I'm using this point and this point. So it increased. Well, if I subtract those, it looks like over those 2 years, we increased by $500 in our GDP, right? We went up. Increase of 500. But how long did it take? Well, it took 2 years to get that increase. So that's where we need to subtract the x values. 1940 minus 1938 means over this 2-year period, we increased by $500 my GDP, or for an average rate of $250 billion per year. Remember, slope is a rate. It's telling you what's happening over and over and over again. So for this little stretch right here, on average, our GDP increased by $250 per year. $250 billion per year. Okay, that's my slope value right there for m. So now let's use our value for m. Let's use our x value that we're going to use, 1940, and there's my y1 value, we're going to use 1500, and we can write a function now. So that linear equation right here, I'm going to use, we've used g, we've used f, let's make this h. So my function h, the third piece, is equal to, it increases at $250 billion per year. X minus, we're fixing it around to 1940. That's my specific x1 value I'm using. It's not squared, so I just leave it like that, right? It's linear, so it's a straight line. But if I'm fixed around 1940, the y value that goes with it is 1500. And there is a linear equation in point slope form. It's a little bit different, but it's an easy way to write a linear equation. All right, so we've got 3 functions, 3 different periods, right? Let's list them all out here. So the first one we had was f of x equals 15.625 times x minus 1932 squared plus 750. That was this first part right here. And then we had the second part, g of x. That equation was this part right here. And that was negative 100 times x minus 1937 squared plus 1100. It's negative because it's opening downward, whereas the other one was opening upward and positive. Finally, we had our third function, the linear one, h of x. And we had a point slope form. We had 250 was our slope. And we centered it around at this point, 1940 plus 1500. And there we go. Now, some things, again, with pieces, we have to make sure that these are all one function. So when we do a piecewise function, we might call this like, we might call this like L of x. Let's just do L because I can't think of any one. So we have L of x is all one function composed of 3 different functions. And then we need to define when to do each function. So we do function f. This first function gets used between 1929 for those x values, but less than or equal to 1936. We use the second function between 1936, those x values all the way up to 1938. But then we use this last function from 1938, all the x values, that should be equals, all the way up to 1940. Got a little sloppy there, but the point is, in a piecewise function, you need to tell which x values that function works on. Then when you put them all together, you're all covered. You're not overlapping, you're not getting like a really messy one. This one clearly goes and stops here, then the next one starts, then it stops, and the next one stops. So there we go. Well, let's take our functions, let's go to our Desmos calculator and see if they actually look legit, right? We just kind of made these up from some points, but let's graph them and see how it compares. So let's pull up our Desmos calculator and do some graphing. All right, here we are. I went ahead and I framed the window so that it covered from 1928 to 1940. And I made my gross domestic product from 0 up to 2000. So it was similar to the graph that we were working with. You got to be able to see the right parts of the graph. Again, on your to adjust that, go to graph settings, and you can adjust your x and y axis. Again, year, my y axis was GDP in billions of dollars. There we go. So we're even labeling my axes now. It's good stuff. Now I've got my functions already put in. So remember f of x, there's my function. And on your Desmos calculator, if you want to designate a certain piece of it, what if I use these little curly brackets, I'm telling it to use this function for these x values. Start at 1929. All the x values bigger than 1929, but less than or equal to 1936. If I turn it on, you can see that there we go. It starts right here. And it goes, there's my vertex. We use that in our equation, right? 1932, 750, 1932 and 750. And then it increases, but it stops right here at this point. Because then at this point, we're going to use a different function. So let's turn on the function g. And as soon as it transitions, now we've got a new function making sure it goes the other way. Again, there's my function, and I had to tell that one to work from 1936 up to 1938. But then after 1938, guess what? We switch again and we go to that linear function. And so now you can see there's that line showing the increase of the economy from 1938 on. So that's how you do piecewise functions with your Desmos calculator. You just tell really specifically what x values you want it to work on or don't want it to work on. So we did our total function, and you might have already guessed, but what did we just graph? Well, we graphed the Great Depression from 1928 to 1940. This was a really marked time in the US history, right? Things crashed hard in the 30s. Things were great in the 20s, and then all of a sudden you see things plummet, plummet, plummet down. And all this area, it took a while for us to get out. We kind of worked our way out, but then we had a little mini recession right here. So things were low and low and low. This is the Great Depression area. So we actually graphed real events. 1940, this is when we started to get into the World War, and it really spurred on a lot of things. And so we see that we started building planes, we started building automobiles, we started building a lot of stuff in the 40s, and then the 50s and 60s were this big economic period of a lot of growth. So anyways, this is what we just graphed. We just graphed this parabola, and then we graphed that parabola, and then we graphed that line. And these were actually time periods. These are measured statistics from our US history. Now what's interesting is we went through kind of another little mini depression, right? Or Great Recession. And if you look at what's happening, there's some similarities. If we look at it, we have a little parabola here going on, right? So at 2006, at 2007, there's my vertex. There's the maximum value. That's when things peaked. Things were really good. And then they kind of dived in 2008 and 2009. We hit rock bottom. And we've slowly been kind of growing our way out. But this is kind of a linear part right here. Whereas this is another quadratic part, which is just interesting because it compares a lot with the other graphs. Let's put them side by side. You can see if we just focus on this, a little quadratic portion, we hit a maximum value, we grow, we hit a recession, it declines, and then we work our way out. It's similar to the one that we just experienced before. So if you think you're an economist, or if you're a person in charge of making economic decisions, you kind of notice this stuff, right? You want to use math to look for trends and patterns. You want to know, are we at the top of a bubble? Are we about to head into recession? Are we still growing? When is the point of stopping? So we want to look for similar patterns. Similar patterns of economic growth by using our maths, using functions, using piecewise functions. We can better understand what's happening. We can better predict what may happen in the future. All right, so let's wrap it up. GDP is an important way to measure the growth and health of a country, gross domestic product. We can see similar patterns. We can use our math, our graphs, to see patterns of growth, recession, and recovery throughout the history of the US. In fact, there's certain periods where it seems to have quadratic growth, like a parabola, and there's certain times where we see linear growth. Being able to use mathematics, such as linear and quadratic equations, helps us understand these patterns of recession and recovery so that we can make better financial decisions as a country. All right, so what do we cover? Again, we talked a lot about how changes in economic conditions affect this idea of real gross domestic product. We generalized the business cycle as a piecewise function. We looked at the Great Depression, right? Broke it down into 3 functions. We discussed the business cycle in terms of a function. So there's places of growth, there's places where we peak, there's places of recession where we decline. We found the extrema of a function, maximum and min values. We used it to compare economic conditions. All right. Hopefully this was a good, helpful video for you to understand better economics and how math plays into understanding economics better.